Did you already email your?
Yeah. Should say
Fabric
yes.
seal. Excellent.
Is there a link? You put it on
You
the
could,
slide.
so you had videos. Okay. Latest. Perhaps I can download it. Do you want to use the browser?
Yeah, it will work.
It works.
Yeah.
Okay. Presentation mode. Excellent. So, Team 9, I have to say we have had 3 great presentations, 3 great projects, 6, 7, 8. They raised the bars, and I'm personally very impressed. Now we have Team 9, where Banu, Fabricio, Pujit, Ryan, and Shayak. They are going to talk about design and control of a built quadruped platform for assistive mobility. Please, Fabricio.
Thank you. So let's start discussing a little bit about our HAT model. Well, all around the world, there are millions of people that suffer a stroke. That means that they have to deal with reduced mobility during their daily lives. Because of this reason, these problems directly affect the quality of movement during the gait cycle. But there are different wearable devices that aim to help this problem by increasing the efficiency during walking, like the passive wheels. In our project, we want to focus. We're replicating and evaluating this concept in a quadruped robot.
Yeah, so the baby model in her controller was that the original problem statement was for us to use like a modified NPC that would have modified constraints to include wheels for like a already existing model of a quadruped. So we started off with like a similar model, and we decided to use constraints to include our like the variation that comes with maybe a taxi light. So we'll still be using the same linear inverter pendulum model, which just assumes the entire mass of the body to be concentrated at the center of mass of the body, and like a pseudo pendulum that attaches the COM and the ZMP to the 0 and 1 point. The MPC we used, I think like the previous team gave like a really good introduction to MPC. But yeah, it's pretty much the same. You're using the state and the action as a control of actions, and using a linearized model to get the newer states. We start off with this. The way MPC works is that it looks at a receiving horizon, right? So at each time step, it looks until heat time steps forward, and it starts off with random actions, and it throws it into the linearized model and gets the next stage for the next key model, key time steps. Then what it does is it uses the next state and the actions to get the cost using the cost function. The cost function is kind of important because that's also where we'll be including our constraints. Yeah, go back a slide. So since we already have another way, as we previously established, to get the newer states with respect to the old state and the action, you can just substitute that in this function. And so we can get the cost as a function with state and action at its step. Once we do this, we try to minimize this by changing the actions, because that is the only variable here, and the state itself can be given as a function of the previous state and the action that is going to be taken on. This can be done in a lot of ways. You can just use a solver, but the most efficient or most commonly used way is a dynamic programming type of solver. I don't have time, so I won't delve deep into it, but we keep doing this iteratively until we get a optimal action set. Once we get the optimal action set, this trajectory is returned to the controller, and the controller takes just the first step. That is a brief introduction of the MPC that we implemented. I'll be moving on to the methodology.
So to explain everything which Bhanu just explained to us, the methodology which we are implementationally have made for this is that we first load the parameters and we initialize the dynamics model. As explained, we initialize the MPC controller, and then we first just ensure that the robot is stabilized in a standing position, and that's when the main control loop starts. So the main control loop ensures that we get the robot state. We have a gate generator. We basically have tested our algorithms with two different types of walking modes. One is simple walk mode and the other one is trot. So it generates the pattern of leg movement, from which we then generate a reference trajectory. We already assume the target velocity which we want the robot to move forward, which is used to generate that. And after that, we have a few low-level controllers which are calculating the IK for each of the legs depending on what state they are in. They are either in a swing mode or a stance mode, either in contact in the leg or either they're in the air. And at the same time, we have the MPC controller pretty much as explained earlier, which is giving us the contact schedule, solving the optimization, and then outputting us the optimal contact forces. All of that is then like combined and then given to our low-level PD leg controllers to further move the robot. And the way we have implemented is that we can either switch to either a normal quadruped with no wheels or a quadruped with additional thrusters on four ends to utilize some of the upper actuation which we can ideally mimic in an exoskeleton and stabilize our robot to walk with wheels. If the condition is that the thrusters are enabled with wheels, it will again share a little bit of the weight ratio by actuating the thrusters, or else if it's just a normal normal legged quadruped with no wheels, it will just move the robot, log the data, and for now we have like run this for a specified time duration. So if the time is run, then it will just end the loop, or otherwise it will repeat the entire loop again.
The wheel design part, the direction for the design was mainly coming from the way we were using our control structure for the robot. So essentially, we wanted a wheel to mimic a foot when it was trying to move forward, and also like mimic a wheel, but a passive wheel when it was trying to roll forward. So we kind of like got the inspiration from roller skates, where like you would like use your legs to propel yourself forward, and then you stop propelling, and then like you roll forward because of inertia. So that was the main motivation for the design. So for that, we came up with two designs. One was this first one where like the wheel was a bit larger, and then we tried to put it on the robot. But since this was long enough and did not go well with the robot, we came with the second wheel. And this was basically a one-way ratcheting wheel. So the idea was you basically like try to move your foot forward, and this thing will behave as a rigid foot. But as it keeps rolling forward, it's like free to rotate in one direction, and then you could like achieve that roller skate rolling after you like try to propel yourself forward. So that was the main goal for that, and for which I will like tell the results.
So these are the results which we achieved in control for Mojoko. First, we are going to demonstrate how it walks in walk and trot mode without any wheels, because we essentially are trying to compare our results, how it acts with wheels, and that's why we made the entire control flow for that. So you can see on the left, it's just walking in normal mode, and to the right, it's walking in trot mode. If you pay close attention to the leg movements in both, you'll be able to differentiate what exactly the difference is in updating the gait pattern for them. So we could make it move steadily in one direction, and then we can do the same thing with wheels as well. So we further added our passive wheels, and then we added 4 thrusters on the corner, as you can see, to stabilize it and move it forward with wheels and implement the same walking generation for both walk and trot modes. And you can see that it walks successfully in wheels as well as thrusters in both walk modes, with like one leg movement at a time, and in trot mode as well, where you can see that it's lifting 2 legs at a time to propel itself faster. And since we have the baseline comparison available to us for both cases, we can draw out if whether our proof of concept works. So for that, we take the torques exerted by the robot in its thighs, because realistically that's like one of the main pressure points you would walk with. And you can see that with our wheels and our thrusters, the torque is like really majorly reduced, which further corroborates our assumption that whatever we are trying to do is gonna eventually help us create mobility devices. And also, if we just take a look at the pitch angle for trot motion, if you could remember how the robot walked in the video, it will have like a little bit of offset. And with thrusters and wheels, we can see that even the amount of offset has been reduced, which further strengthens our reasoning that whatever we are trying to do can lay the baseline for creating exoskeletons and passive wheel designs to help people walk better.
So before to continue with the real life test that we did one last simulation with the spot quadruped robot from Boston Dynamics, where we attached some passive wheels on it. And we could see that this in these simulations, the robot was able to walk as well to balance. And then we continue with our real life testings, where we could see that when attaching the wheels on the robot, it was able to walk. However, we identified 2 main expected problems. The first one was the material used for our wheels. In this case, this was also a limitation that we had, as we were using the PLA printed, 3D printed material from Space Maker, or the Makerspace from the university. And then we also observed that the design that we create to on the wheel allow us to easily attach the wheel on the foot. However, we also find out that the wheel moves or directly or completely disappears from the robot. And yeah, these 2 main problems that we find allow us to know what are the future changes that we need to do for further design.
Yeah. So during the experimentation of our project, our proof of concept, which is the wheel design, successfully demonstrated its core idea, which is aligned with a model, and that is with the combination of actuators and wheels, we could actually reduce the strain during the leg movement. And so with the combination of mechanical supports paired with an appropriate control logic, we could actually we could actually align our project with the HAT model. And then going forward with our future work, we'd aim to do a proper stress analysis on the current design to actually determine exactly the critical points of failure, and then use that knowledge along with stronger, lighter materials to come up with fabrication which is even stronger. And that would be followed by some tweaks in the control logic to accommodate design changes.
Yeah, that's all. Thank you.
Very great. So, questions from Team 9. Looking for three top
Did
questions.
you try developing like a custom gate that uses the wheel to like roll the robot, sort of like a roller skater would?
That was our original idea, but that proved a lot more complicated than we initially estimated.
So like just to get to this stage, we had to really
My
encounter
question
a lot
is
of
sort of
problems.
related to what Arjun asked. At least from what I remember from those days that I had roller skate skates, you don't have this locking mechanism in roller skates, correct?
Yeah.
They can passively rotate clockwise and counterclockwise.
Yes.
So how is that we can get meaningful mobility
Yeah,
on roller skates, and here you have to lock them?
So that's because of the way
So-
how many degrees of freedom we have at our foot, right? So if you can like draw your foot a bit, and then like that would like act as a rigid support, and then it would like push against the normal direction of the wheels.
So,
Are you saying this is because of the
you know,
number of degrees
so
of freedom?
the robot,
Yeah.
the robot cannot yaw. So when you skate, you use your leg to yaw, and then push yourself.
So you use unit 3, and unit 3 cannot yaw?
No.
Legs?
The robot dogs cannot. So we did come up with an idea where the wheels itself are like, sort of like these. It was already yawed.
Well, that we call it pronation supination. That yaw.
Yeah, like we
That's
just,
the- that's a good
yeah,
point,
so
because
in
we
for
can
the
use it
front legs,
to sort of anchor and our leg on the ground, right?
A go-to with like wheels built
Yeah, these are passive. That's an active wheel.
Yeah, those are actually good. They were trying to sort of explore the potential, like, performance enhancing mechanisms as a result of using passive wheels. And they did great work. I'm impressed. Like, you did simulation, you did CADing, prototyping, experimenting. I have tons of questions, but I want our students to answer.
Is that on the robot the built-in controller from the go-to, or did you implement a custom controller?
For real experiments, it is the built-in controller,
Okay.
and for simulation, it's assistive controller.
Oh, so you show in simulation the robot can walk
Yeah.
with the wheels.
Yeah.
But then you said like it's too complicated using
Yeah.
the rolling of the wheel.
Yeah,
Okay.
that's their argument. And you also showed that with wheel versus without wheel, the actuation torque reduces. What is your justification? I mean, beside, like, why do you think this is happening?
Yeah, so if I just pull the graph again. So the left graph is basically a comparison of the total torque on the hind leg thigh joint. And this is happening because of the thruster actuation. So we can basically let the thruster take a portion of the body weight so that it's easy for the robot.
Oh,
to
you're also
stabilize.
using the thrusters?
Yeah.
Based on muscle?
Yeah, yeah. So
Okay.
that's why the torques on the left with the wheels are a lot more lower. And if we look at the base pitch angle in the trot motion, that is because of the effect of wheels. So because wheels essentially give you a lot more stabilized ground to roll, that would give you a lot more of a streamlined motion than like this instead. So that's where the effect of wheels is highlighted, where you can see that the deviation of pitch is a lot more lower with compared to normal feet.
Okay.
And we basically say that the way this can translate it is that if you make an exoskeleton which is sharing your body weight and has passive wheels, you can lay the groundwork for some really cool mobile devices.
Okay, cool, excellent. I think we don't have time for more questions, but this was a great presentation, thank you. So our last team today, Team 10, please, I think, you sent the, okay. And while we are setting up the last team presentation, those of you who have not yet submitted your trace evaluation,